Welcome to Unit 8, Lesson 6, the first derivative test. Remember from the last lesson, when the first derivative is positive, the function is going up. When the first derivative is negative, the function is going down. We can use this to help us figure out maxima and minima. So an extrema is just anywhere there's a maxima or a minima. A global extrema is the highest point everywhere or the lowest point everywhere. A local extrema is only for an interval. For example, there's this image. In this image, we see that the graph is going up and then down and then up and it goes down again. Okay? Well, this graph has a local maximum at this point right here, the first point, because it's going up and it's going down. And then it has local minimum because it's going down and then going up. And then it has a global maximum because the highest point everywhere is on this point. And then as the function goes to negative infinity, that's the global minimum. Okay. So the first derivative test can be used to find all global and local maximum and minimum. For example, if the derivative changes from positive to negative, so on the left-hand side it's going up, on the right-hand side of a point is coming down, then we know it's maximum. If the derivative changes from negative to positive, so on the left-hand side is coming down, on the right-hand side is coming up, then we know we have a minimum. Let's look at two examples. Example 1. f of x equals x squared minus 4x plus 3. So step 1, we find all the critical points. The derivative is defined everywhere. Let's find it where the derivative is 0. f of x is x squared, so the derivative is 2x. Minus 4x, the derivative of minus 4x is minus 4. Plus 3, the derivative of plus 3 is 0. So the derivative of f prime of x is equal to 2x minus 4. 2x minus 4 is equal to 0 when x is equals to 2. So the critical point is at x equals 2. Now we want to check to see if our function is increasing or decreasing. In other words, whether our derivative is positive or negative around x equals 2. So in the interval negative infinity to 2, let's try x equals 1. When x equals 1, the derivative is negative because 2x minus 4, 2 times 1 minus 4 is negative. So that means the function is decreasing. In the interval 2 to infinity, so when it's larger than 2, let's try x equals 3. Well, when x equals 3, the derivative 2 times 3 minus 4 is positive. So the function is increasing. Since the derivative is negative to the left of our critical point and positive to the right, by the first derivative test, f of x must have a maximum at x equals 2. So we know our graph must look like this. Whoops, that would be a minimum. Let's try this again. It should look more like this. Yes. Actually, I drew this correctly. Again, sorry. Let's draw this. I made a mistake here. What mistake did I make? Well, we know that the function is decreasing to the left and increasing to the right. If that's the case, our point must be a minimum, not a maximum. So f of x has a minimum at x equals 2 by the first derivative test. Example 2. G of x is equal to 1/3 x cubed plus 4x squared plus 15x plus 1. Let's take the derivative. That gives us x squared plus 8x plus 15. This is 0. Well, we can factor because that's equal to x plus 3x plus 5. So the derivative equals to 0 at x equals -3 and -5. Now let's think about what the derivative looks like in our three intervals. We have from -infinity to -5. The second interval is -5 to -3. The third interval is -3 to positive infinity. So when x is less than -5, let's try -6. The derivative is negative times negative, so it's positive. So our function is increasing. Let's start sketching our graph. So here are our axes. We know that before it gets to -5, our function must be increasing, like this. And then when it gets to -5, so now we go from -5 to -3. Let's try -4. The derivative is going to be a negative number times a positive number, which is negative. So our function must be decreasing between -5 and -3. So if this is -5, this is -3, we know our function must be decreasing somehow, like this, when we sketch it. Next, from -3 to infinity, let's try 0. Let's actually, 0. Our derivative will be 3 times 5, which is positive. So our function is increasing again. So that means our graph for f of x should look like this. Starting at x equals -3, it starts increasing again. Okay. Let's check our function to see if it's right on decimals. So y equals 1/3 x cubed plus 4x squared plus 15x plus 1. Okay. And sure enough, we see that our graph is increasing until it gets to -5, decreasing between -5 and -3, and increasing again after it passes x equals -3. Okay. So therefore, g of x has a maximum at x equals -5 and a minimum at x equals -3. Okay. Finally, I should mention that sometimes our graph is unusual, but our graph could have a negative slope, and then has a 0 slope, and then it has a negative slope again. Or it has a positive slope, and then 0, and then positive slope again. When that happens, it's called a saddle point. That's why just because we have the derivative of 0 doesn't mean that it's a minimum or maximum. We have to check these intervals to make sure that it's not a saddle point. Okay? That's it for this video.